Hello everybody and welcome to Saturday Morning Coding. As you know, we are starting today a new project. Sorry that I forgot to change the text. I'm gonna changing the text. So it's episode 24 and yeah, it was still with the old with the title from the past episode. So yeah. So now here I have an empty Python project, and just to make it more simple, I'm gonna just install Pillow, so we don't need to deal with how to process images and so on. And then yeah, then I'm gonna get couple images. I'm gonna get couple images for us to process. Yeah, I'm downloading them now. They are black and white images, but yeah, without copyright. Okay. This, for example, I don't understand. Okay. So we have these two images, and I think that that's enough for test. And yeah, now we are gonna start creating our library. The aim of this library is not to be fast, it's not to be perfect, it's just to show the basic techniques. So yeah. So these are the test images, and I have installed, as I said, I have installed Pillow package, just so we don't need to deal with loading the images and so on. We just open the images with Pillow, and that's it. So now we create a new Python package here, and I call it PI, for example, which is going to be the name of the library. And the first new package inside, and this is going to be, I'm going to call this package blur, because we are going to explore at least one type of blur that we can apply to the image. Yeah, and then another package, new package, which is gonna be utils, that are gonna be for different utilities that will be used throughout the whole thing. And we are gonna start by creating new file named convolution. What is a convolution? It's basically applying a matrix to every single pixel, getting to know modifying every pixel based on the neighboring pixels, which is a very common tool. And then in utils, because probably inside Pillow there's utilities for many of these things, but I want to create them from scratch. So I'm gonna create color, and we are starting with color. So the first thing that I'm gonna add to the library is yeah, this shouldn't be called color actually. I'm gonna call this refactor color utils, for example. Yeah, and we will see later about this. I want to first save, delete. So first is the color utils. So the first thing that I want to create is a function that converts an RGB color into a grayscale color. So RGB to gray, and this receives an RGB color, which is a tuple, because Pillow represents the colors as tuples. We will see how this is done, and this is gonna return tuple. I wonder if you can say integer or int. Yeah, int. And this is our function, and then we are gonna do this. This is the first thing that there's many ways of converting a color to RGB. Now, there's many ways to convert these colors to to convert a color to RGB, but I'm gonna call this Luma RGB to gray. So an RGB color to a grayscale value, which is the luma component of the color. Then there is this, there's even different types of luma. This is luma represents the brightness. That's why it's used to calculate grayscale values. But there's even definite different types of luma calculations. Let me. It's the luma component of the color. We need to stick to standard. There's not gonna be so much difference, but there can be some difference. So let's just stick to the standard. According to CCIR 601, okay, this is the old name, so now it's from the ITUT recommendation 601 BT dot 601. And basically this is just a formula. There's a lot of physics behind it, but we don't need to get into that. So so the luma component, I'm gonna call dt dot 601 601 luma. We could make this in a class, but there's no need, because basically in a supposed class there would be all the static methods anyway, so we can just create functions anyway. Function name should be lowercase. Luma BT 601. We don't need to say that it transforms RGB to grayscale, because that's a given if it's the luma. So then we have the coefficients here. So return 0.299 times the red component, which is RGB of 0, plus 0.587 green component times RGB of 1, which is the green component, plus 0.114 times the blue component. And then because we need to return an integer, we need to round, because obviously this may not be a round number. So now we can come to the Python console and do a couple tests. I'm doing it in Python 3.8. It's still, I need to update this, but it it shouldn't matter. From spi dot utils import color utils. Well, yeah, as cu. So now we have cu dot luma dt601, and we can put, for example, a tuple here. 601 luma coefficients. I'm just trying to find the calculator online, so we can check if this is correct. But the thing, well, yeah, let's say, for example, 25500. This is 76. We obviously have the thing that if the components of the RGB are bytes, this is going to return a byte. So in this case, the RGB components, because this plus this is equal or less than 1, then this is going to be in the same range as the return component will be in the same range as the component of the RGB. So this is the first way to transform color to RGB, and now we can do a test. We can do a test of this, and let's get a CC0 imaging that has color. CC0 images just for test. For example, this is a good one actually. It's so now this is the image. So now in the utils, I'm gonna do I'm gonna create I don't know if this is technically a convolution. I'm gonna call them operator. And yeah, let's apply pixels was, and then here we will have from pil import pixel access. Is it pixel access object? I need to check this. Pixel access object. Yeah, it's pixel access. Pixel access. So this receives a px, which is a pixel access, and then from typing import Python 3 typing. I never remember this function. Typing this is a fn is callable. So now I need to know and this returns known. So yeah, I know that there might be faster ways to do this, but I want to be able to do it pixel by pixel. I know that it's slow, but as I said, this is not. This is the goal of this is more didactic than actually functional. I also want to learn about how to do this properly and the maths behind it. So image model, that size. I think that size. Size. I think it's a tuple, but not sure. So now. Image and open. Image. Yes, size is a tuple, so okay, so this means that for x in range size 0, for y in range size of 1, we do fn of px of x, y. So px of x, y. I don't know why. Okay. I'm gonna consider that this word exists. This bugs me a lot. Say pixel wise to pixel. So here we are applying a function to every pixel. So now we can do a test. We can do our own test here. We will get into unit testing later, but I'm gonna call this main.py, and then I'm gonna do quick and dirty script. So image equals I'm gonna create another folder called out, new directory out, so we don't mix images from import pin dot no, I don't know what I'm doing anymore. From if from field import image image.open dot test c, then we do dx equals im.load, and then we import from operators from spi.utils import operators, and from spi.utils for spi.util.operators import apply pixel-wise, and dot color utils import luma vt601. So now we do apply pixel-wise, and then px im dot size luma vt601, and this I'm not sure if this is a function, a method, or a property, so I'm not sure. And now we im dot save test out dot test c black and white dot jpg. So now this should apply this luma function to this to every pixel in this image. Let's see. Let's execute this. Run main. And import pixel access from pil. Okay. In which package it is? From pil dot image import pixel access. Let's see. Pil dot pixel access. It's a class, so I'm not sure in which pixel access class, but in which I'm checking now so it's pil search area pixel access this repository. Okay, from pil dot by access import by access. Okay. As you can see, it's slow. Now it's finished. Oh, of course, this is the Luma, but the Luma has translated to the yeah, this Luma has translated to the red channel, so we need to fix this. But yeah, because this considers that that this image, yeah, if we could do this, because we know that all the grays are the grays have the same value as RGB, so if we want to do it in the same in the same function, we need to grab the luma function def grab luma grab. The other option would be to convert this image to a 1 byte per pixel image, but yeah, that is not how it goes, at least not for now. So we receive a RGB and this is a tuple, and we return an integer, no, another tuple. So so we do value val equals luma bt601 of RGB, and then we return val. Yeah, the parentheses are redundant. Yeah, and then instead of luma, we do luma grab. Okay. So now it's black and white with the luma component. Don't get fooled, because this image, even though it is black and white, is still a color image, because it has 3 pixels per 3 bytes per pixel, and it still has 3 channels. So this is not truly an RGB image, but serves to fit the idea of what is the luma. So this is the original image, and this is the luma. So obviously the lighter the luma, and it follows this recommendation of the ITU, the International Telecommunications Union. And yes, this is still having 3 channels, and it's not a black and white image, but yeah, it works. So it's apparently black and white, and you can see that the size of this image is humongous. So that's why it takes so long. So now we saw how can we use this luma function to create this. So now the next thing, utils, color utils. Based on this, we can code a function that does convert to RGB and returns an image. So returns an image that it's truly a 1-channel image. So it's truly a black and white image. So we do file conversions. So we can do and do RGB gray, and then we receive here from fill import image, receives a 3-channel RGB color image and converts it to a 1-channel grayscale image. So this from import image, and then it's in, which is an image, and then it returns another image. Now we do R is gonna be my image, and it's gonna be image dot new mode L. I need to check this, but L is 8-bit pixels, black and white, and then you need to I think it's size and color. So this creates a size with the in.size, and we can create it with color 0 by default. And then zero in size that 1 for Y, and then this is R of X, Y equals import color dot color from dot color utils import, I don't remember even how I call the function, Luma of image of X and Y, and then you return R, which is a new image. And now in our main we can test black and white equals from spi dot utils import dot conversions import RGB gray. Black and white is RGB gray of the image, and then we save this as true. Oh, yes. Conversions in px is equal to image dot node r dot px is equal r dot load px equals you need to load the pixel access object. So now I think that our main is right now. It's slow, but we are not caring about that. We are not saving the black and white image, obviously, so okay. Now we have a true 8-bit color instead of this, which is 24-bit color. This is 8-bit color. So this is a true black and white image now, and you can see as well in the size that is slightly smaller. Keep same size, but this is 8-bit color and this is 24-bit color. So some image only containing black and white or grayscale pixel colors doesn't mean that the image is 1 bit per pixel, obviously. So yeah, now we have a way to start manipulating images. So now the next thing that we can do to improve this this image library is to start to add operations to it. So now we have gray images, and we can do, yeah, I mean, of course, here in conversions we still need to say if image dot there should be mode yeah, this class is huge. Yeah, if image.mode is different from what would be a 24 byte per pixel, RGB, then we raise an exception, invalid, no, value error, the original image must be RGB. So if I do the main now, so this still work because this image is RGB. and this should still be the same 8-bit color, 24-bit color. So yeah, so now we yeah, we have our operators, apply pixel wise conversions, RGB to gray, color utils, and then yeah, I think that blur okay. So for blur we can start with the easiest type of blur. I'm gonna explain the concept on the iPad. So what we are implementing now is this thing called a box blur, which is the most basic type of blur there is. And it's also called a linear filter, but essentially what this means is that for every pixel um, we apply this. This would be size 3 box blur, and this means that we have if this is the pixel we are modifying, we sum the values. This is considering that there's only one channel, right? So we sum the values, all the values, including the one that we are processing, and divide by 9. So this causes that the pixel that we are modifying gets the average of himself or itself and all the neighbors, and this causes blur. I don't know if you have been able to see what I have been drawing. Have you? What? Well, it's technical issues. Okay. Okay, now. Yeah, basically this is it, what I was explaining, that that you basically set every pixel to the average value of himself and all the neighbors. and that's it. And you do this for every pixel in the image. And this is called 3x3 box blur. So let's implement this now. Of course, this only applies for when there is a for when there is a like a single channel image. So we import from field import image. I'm gonna call this gray box blur gray, and then we receive im as an image, and we return an image. And we could do the apply pixel wise. Yeah. We could use the apply pixel wise, but we are not gonna do this now. We are in the future. We are gonna create this type of way of traversing the images with the neighbors and so on, but not now, not yet. So in pixels, first we load the image. Image.load, so we have the pixels now, and then for x in im.size in range im.size 0, for y in range in size 1, then do actually we don't need to return the image. This can be done in place. No, actually it cannot be done in place, so we need to copy the image. Actually, we don't need to copy the image. We need to do the return image is image.new mode L, size is image.size, default value is 0, and then the pixels from the result image is x r equals r dot load, and we do this on top, and then we need to get the neighbors, and this, yeah, we can do this by hand, but I think that at some point we will need to move this to a util, because this is quite a common operation to get the neighbors of a pixel. So yeah, how I should do this? Yeah, for new x if in range x minus 1 is x minus 1, x plus 1, but it's not included, so it's x plus 2 for ny equals y minus 1, y plus 2, and then sum equals to 0. Total, let's call it total. So if nx is bigger or equal than 0 and nx is smaller than image dot size 0, and now we need to do the same for the y. Count equals 0. Ny here and ny here. Then total plus equals oh, interesting. I never remember that this is possible. So zero in nx and 0 in y. Then total plus equals the original image. So pixels of nx and y, count plus equals 1, and then the new image pxr of x and y equals round total divided by count. So now this takes all the neighbors and calculates the average value and puts it into the current pixel, as explained. So now so the black and white equals, of course here we need to check in this box blur, because we if im.mode is not L, then rise value error image must be grayscale. So now in my main I get this image, I convert it to gray using our utilities. Test C blur. So now I get new image equals from spi.blur import dot box spi.blur dot Did I mess it up by factory name? Box blur import box blur gray, so the new image is box blur gray of the black and white image, and then we save the new image. It's taking its time. Is it even in a... I wonder if it's I wonder if it's oh, I don't remember. I don't return anything, so I need to return the new image. Return. Oh, no new line. Yeah, I'm gonna debug this to make sure that it's running properly. I didn't click debug. This is extremely slow though. It's because we are doing this pixel access all the time. So now we have managed to convert it to gray. So now we have another image. So it seems that it's doing it properly. It's just extremely slow, which is to be expected. So now we wait until it finishes, which means that we'll stop here in save. Just extremely slow. Which, as I said, is to be expected. Yeah, it's still executing. I mean, this image is huge. It has like several million pixels, so it's to be expected that it is pretty slow. Yeah, when we are able to downscale the images, then we will be able to work with smaller images. Come on, I want to see the result as a closing for this episode. Okay, 337252528. The x needs to go up to 2448 and it's in 400. This may be a little bit of an overkill. We should work with smaller images. And also it's debugging, so it's even slower. Okay, almost half. We are getting there. If it fails, I will cry. Of course, this is not, as I said, this is to learn. This is not the real way to do things, because pixel access like this is very slow, and all these loops are very slow. This is like a quadratic order, so it's everything is slow. So don't take this as an example of how this should be done, but just as a way to learn. So maybe it would be good to use smaller images, but we are gonna do downscaling in next chapter, so we can work with the smaller images. Yeah, we are now half. Yeah. In the meantime, because it will stop when it needs to save, Yeah, there's a lot of pixels here to process, so patiently waiting. But yeah, downscaling is necessary for these images. I'm downloading an image that is way too big for the speed that we can achieve this with these basic techniques. 1800. Yeah, as you can imagine, this is an operation that could be parallelized because you modify only one pic, the original image stays untouched, and you just read from it, and the pixels of the new image are independent one from the other. So yeah, this is something that could be done in parallel. Okay. Hope that I didn't make any mistake because this is painful. It's painful to wait. Okay, we are going. Almost. Yes, now we are here. So now you can see how, if you zoom, because this image is huge, if you zoom, you can see how the image has been blurred. Let's see, in a place where it's actually easy to appreciate. Like for example here, this is in the top corner. You can see here that it's smooth here, and there's artifacts here. So this is one of the effects. You can see it more clearly maybe if I zoom more. This is one of the effects of blurring, that you make all these artifacts disappear at the expense of, obviously at the expense of losing definition, because you don't do anything with the borders or anything. So yeah, so this is the most basic type of blurring. Then there's more advanced techniques that take different mathematical features into consideration. Something to be noticed as well is that you can see here that you kind of lose when there's a sudden change in contrast. By blurring, you lose that contrast, so the borders become like less sharp, which is obviously the idea of blurring. But yeah, we have eliminated now these artifacts from the image by blurring. Next, in the next session, we are gonna. I hope that the effect can be observed, but yeah, that in the next session we are gonna be working on downscaling stuff, so we don't need to wait for like 5 minutes for an image to be processed. And yeah, one last look at this blur. So yeah, thank you for passing by. This is gonna be as well on YouTube, and um, I forgot to change the title of the stream, but it's too late now. Anyway, that this is gonna be on YouTube, and see you next weekend. Bye.